master's thesis, which was about looking at how rotation systems can impact the carbon footprint as well as the carbon sequestration that can happen on farms, and looking at specifically around how bringing in livestock or changing a rotation system can cause this impact. Okay, just to give an introduction, around the world, the biggest usage of land goes towards agriculture. So most of what we use land for is for growing food crops. Anything that uses this much of the world has to have a massive impact on the environment just because of the amount of space that goes towards it. So when you look at agriculture and greenhouse gas emissions, 25%, just about a quarter of all human-caused emissions are from agricultural activities. So it has a very significant impact on climate change and global emissions. Then around the world, we have an agreement called the Paris Climate Agreement, where we signed it. Over 196 parties signed this agreement, and basically we really want to keep global warming below 2 degrees and preferably to 1.5 degrees Celsius, which is the amount of warming. So it's very critical to be able to develop the ways in which we can farm that aren't contributing more emissions, but are being able to produce a lot more food without increasing climate change. And then another important point is when we look at ways of how to mitigate climate change, sequestering carbon on farms is seen as an important mitigation strategy. So it's not just decreasing our emissions, but also how can we sequester carbon into the soils and onto our farms. So basically, to look at all these things, I looked at crop rotation systems and how you can use the choice of which crops you plant to create an impact. So why crop rotation? So crop rotation, you can use it in any context. It's an accessible technology, which means you don't need to have a lot of money to invest in it necessarily. And your choice of what you choose to plant in it not only affects the way you manage it or which inputs you have to use, which impacts the carbon footprint, but it also impacts what we call the agro-ecosystem. So an agro-ecosystem is an ecosystem that we use specifically to produce agricultural products, and it refers to a farm, but also the areas surrounding it. So basically, what is the land doing when we manage it? So by using crop rotation, you can reuse one resource multiple times, and we call the circular economy. So when you are growing a wheat field, for example, and after you've harvested, you have a lot of residue. You can then reuse that a second time, that residue that's left behind, as an animal feed product. So it's all these ways that you can connect the rotation together and create what we call links, and through that you can be more efficient and reuse your resources. Other benefits are also being more resilient. So this means for climate, for example, if you have a very dry year, or maybe there's more economically resilient. So if the price of something goes up or the price of an input goes up, then you can quickly adjust your production system and use that flexibility to your advantage to be able to weather shocks better. And then just some examples of how rotations are used. For example, using legumes in your system. If you can use a legume to fix nitrogen through the symbiotic with rhizobia, then you don't have to apply as much nitrogen. So that's a direct link of how rotation can impact the way you manage all your other phases. Another example is livestock incorporation. If you incorporate livestock, it not only is there something now feeding on that land and that biomass, but there's also manure and excreta going into that system and you're cycling nutrients. And then another example is high diversity. So having a high level of diversity and having less monocultures is associated with being more stable as a system, and you're also going to increase the amount of resilience you have against a pest coming in or a disease. So the three things that I wanted to specifically answer in my study, and I looked specifically in the Swartland region, so I was at Lankelben's farm, and this is a dryland area which produces wheat, canola, also sheep on meadow pastures, and also lupins and some other crops. The first thing I wanted to know is, how can these systems be used to sequester carbon? So how can you use these farming systems to suck carbon dioxide out of the atmosphere, which is a greenhouse gas, and store it into the soils? And is there any difference between different rotation systems? The next question I had was specifically around soil greenhouse gases. So there's greenhouse gases that, when they occur in agriculture, there's different places which emit them. The first one is through the inputs that you use. So anything that you use on your farm that uses any fossil fuel inputs, so any electricity, any diesel, and anything that you bring on that was manufactured using those inputs. All of those will have a carbon footprint. Anything that's transported, the fuel you use in the transport, all has a carbon footprint. And these are almost what we call indirect emissions. So although they don't happen on your farm, they happen through the making and the transporting and creating of those products. The second kind of emissions happen directly on your farm, and these are called direct emissions. And if you could see greenhouse gases, you would physically be able to see them leaving your field or leaving your tractor and going into the atmosphere. So these emissions, and a very important one, is the emissions that come directly from your soil. So the most important soil emission is nitrous oxide. Nitrous oxide is one of the greenhouse gases. There's also carbon dioxide and methane. And what nitrous oxide does is, if there's too much nitrogen in your soil, or if there's extra nitrogen, then it forms from that and then it gets released into the atmosphere, directly out of your soils over the entire year. So the next thing I wanted to answer was, how is the nitrous oxide impacted by the choice of crops that you plant, as well as the management of those crops? So different crops require different amounts of nitrogen and different forms sometimes. And how does that management and the crop combined impact nitrous oxide? The third question I wanted to answer was, now when you look at all the systems overall, you look at the soil emissions, you look at the carbon sequestered, and you look at all the inputs. Now overall, how do the global warming potentials of the different systems compare? In other words, which system is releasing more emissions and which one is releasing less, and how does that relate to how much each system can produce? So I looked at 3 specific rotations. First system is 3 years of wheat and 1 year canola. So all these systems are 4-year systems, and this is a fully cash crop system. So it doesn't have any legumes or any livestock incorporated, and the applications rates for synthetic fertilizer is 87 kilograms of nitrogen per hectare for wheat and 80 kilograms of nitrogen per hectare for canola. The next system we also looked at was wheat, canola, wheat, and then a cover crop year. The cover crop year is a very diverse year. You don't harvest from it directly. You plant a mixture. In this case, it was a mixture of different grasses, forage grains, and also legume species. And then the last system was a fully livestock incorporated system. So in this year you have alternating phases. So the first one is a cropping year, so you plant wheat, and then the next year it's a livestock on a meadic pasture. Then after that it goes to canola, another cash crop, and then back again to meadics with sheep on it. And this one is mostly reliant on nitrogen fixation. So the amounts of fertilizer we're applying on this system is 26 kilograms of nitrogen per hectare for wheat and 48 kilograms of nitrogen per hectare for canola. So it's significantly less than the first system. And then the cover crop system has a slight reduction in nitrogen the year after the cover crop due to the legume activity. Okay, so just looking at these rotations like this, we can already see that they have a significant difference in the amount of nitrogen, which is definitely going to impact the footprint. So we can see that based on literature and other studies that have been done, there's been an idea that more diverse systems are going to have less inputs and also be more efficient. But at the same time, livestock are associated with being very high emitting. There's methane that comes from enteric fermentation, so you're introducing additional emissions into the system. So it's not about whether incorporating livestock is the best thing or not. It's about how can you balance all these different emission sources to get an overall lower footprint with the highest production. Okay, so basically how did we actually compare these systems? So the first thing we have to do is map up the entire rotation system. We look at all the inputs that went into each system, managing it. We looked at all the outputs that was produced, and we looked at all the processes in between. And anything that would have caused an emission, we take note of, and we basically model the emissions that could have occurred. Then we collected data. The first way we collected data is directly through sampling. So for example, for nitrous oxide or for methane soil emissions, physically going out into the field and collecting gas samples directly from the soil, and that we sent to a lab. The next way we collect data is looking at all the trial records. What are the average yields, what are the protein contents, what fertilizer was used, what pesticides, herbicides, everything. Anything got to do with the record of the trial and how it's managed. Then the last data we collected is through literature. So for example, for modeling something like how much methane comes from having sheep on the property, that we use models from literature, we use emission factors done on other research that when you use that emission factor. And then what we do is we plug all of this in together, we combine this into one big model, and we use what you would call a life cycle assessment, which means you look at the entire life cycle of the system. When you say that when you look at the nitrogen used, you include the manufacturing of that nitrogen and the transport to the farm, and we look at the global warming potential of everything that's used in that system. And then we looked at the emissions in two ways. So whenever you're footprinting anything, there's different ways that you can communicate that footprint. The first one is how much greenhouse gases are being emitted per area of land. So there you're looking at the absolute amount of emissions. What's the carbon footprint per field or per farm? The other way you can look at it is what are the emissions per amount of product that you've produced. So what is the carbon footprint for a kilogram of wheat? And those are two different kinds of footprints, and the one you choose impacts which kind of actions results in a lower footprint. And in this case we looked at both of these together, and because we wanted to see both impacts. Okay, and then so now going into a bit of the results. So the first thing we did is we wanted to look at soil carbon sequestration. So removing carbon out of the atmosphere and storing it into your soil is basically, you can think of it as almost pulling emissions out of the atmosphere again. And it can, as long as the soil can hold onto it and store it and it isn't re-released, you can store that carbon and almost claim it as a removal. So for carbon sequestration, we looked at soil organic carbon values from 2000 to 2021, and we converted all these soil organic carbons to carbon stocks, which refers to the amount of actual carbon within a hectare of land. And when we mapped all of them, all systems showed a significant increase in carbon stocks, which means that all rotations, all three mentioned, were having a significant impact and were all being able to store more and more carbon every year. Now this increase between the systems, they didn't differ significantly between them. So there's slight differences, but it's not what we call statistically significant. So in other words, there's no difference. The rotation, all rotations work to sequester carbon, and there isn't one that's better than the others. Okay, and then when we look at the system, so what we saw is a strong increase in organic carbon. But if you think about it, this whole trial was a conservation agricultural trial. So it means that the principles of conservation agriculture are working, but when we look at the baseline of the farm, where it came from, the reason why conservation agriculture was trialed was because of soil degradation. So in other words, from converting natural land into farmland, a lot of carbon has been lost. So we looked at examples of soil carbon values that occur in natural vegetation that occur there. In this case, it was Renosterveld. So we looked at the values, and we found that between 1.7 and 1.8 is the value of organic carbon that is usually present in Renosterveld. Then when we looked at the start of the trial, the value of the soil in the year 2000 was less than 1%. It was between 0.9 and 1%. So in other words, there's been a very big loss of carbon over the years and over farming. So when these systems were then the trial started and conservation agriculture practices were implemented, so there was no tillage occurring, this carbon begins to come back to the soil. So, and up until now, where it's at 1.4%. So you've almost regained half of what was lost. But if you consider the system over 20 years, which is typically used for carbon footprinting, you're going to see a big increase in carbon and sequestration. But if you consider the system at an almost 100-year level, there's still a loss of carbon compared to the natural vegetation. So we used both of these different, what we call land use impacts, which is what is the impact that farming has on the land and the carbon that's stored in the land. And we got to two different values if you're using 100 years or you're using 20 years. And we wanted to use both of these different values because they communicate different things. So we plugged each of them into a different kind of model. Okay. So, and that's going to go into the carbon footprint when we look at and compare the systems. So the next thing we wanted to do was look at the nitrous oxide as mentioned earlier. So nitrous oxide emissions, I already mentioned, it's very associated to how you manage nitrogen in your system. So in one system, we have a system that's fully dependent on synthetic applications, so that's applying nitrogen to the system. And the other system, we have a mixture. We have a bit of fertilizer, and then we also have legumes, which are fixing it and storing it in an organic form, which must first break down before the plant can access it. And then a third form is through the livestock. So any excreta and manure that's being applied on the field will also contain nitrogen. So for this we use the closed chamber method, which basically is chambers that we put on the field, and we enclose an area of soil, and then we measure the accumulation of greenhouse gas inside that chamber. And what we found was we measured this almost every week for an entire year period, and we were expecting to find most of the emissions occurring directly after you apply fertilizer. What we found was actually the opposite. So very low amounts of nitrous oxide were released. It stayed at a very low level. It was very close to zero, and then all of a sudden, on one rainy day in December, there was a massive spike in the amount of nitrous oxide emitted. So for this chemical reaction to occur, for nitrous oxide to form, you need to have microbial activity, you need to have moisture, and you need to have heat. And you need to have extra nitrogen in the soil. So two of the systems had big spikes, which was the medic and livestock system. So that one is wheat, medic and livestock, canola and medic. And then the other system that also had a spike was the cover crop system, which is wheat, canola, wheat, and then cover crop. For the cash crop only system that relied fully on nitrogen fertilizer, we didn't get a spike at all. And basically the reason for this is by the time it gets to that stage, after you've already had harvest, after the plant's already extracted all the nitrogen out of the soil, there's very little that's being stored in the organic material inside the soil. So when this occurs, when there's water all of a sudden in summer, and it causes a spike in activity in the soil and everything starts breaking down, there's no extra nitrogen that was then released as nitrous oxide. But in the other systems, where you've had 20 years of legumes, there's more nitrogen that's built physically into the organic material. So although all of these systems had the exact same organic carbon amount, the quality of that organic material was different. One of them had nitrogen also in the organic material, and the other one, when it broke down, it was more likely to be immobilizing or pulling nitrogen out rather than releasing it. And then when we also measured methane emissions, but we found these to be negligible. Methane doesn't usually occur in any sort of dry climates. It's usually associated with waterlogging. Okay, and then another thing you have to consider is all of these systems perform very differently. So the amount of yields you're getting in the one system versus the other system on this trial site was very different. So the highest performing system was the wheat and medic system that was half incorporated with sheep, and everything was higher. The biomass at 30 days, 60 days, and also the yields was significantly higher than the cash crop only system. So the cash crop only system had approximately 60% of the yield of the medic incorporated system, and then the system that had 1 year of cover crops, that already gave it a big improvement, and it was about 75% of the total production potential of the highest performing system. Then another thing to look at is not only is there a difference in yields, but also the quality of the wheat. So we looked at wheat protein content over 20 years, and we found that in the system that had wheat and medics and sheep, the protein content remained at 13%. It didn't drop at all, very, very slightly. Then in the second system, which the cover crop system, we found that the wheat protein content dropped by about 1%. So from about just over 12.5 to just under 12. And this was just a very slight drop, but it did make a slight difference. Then the last system, which was the fully cash crop system, had a significant drop in protein content. It dropped from just over 12.5 to under 11% protein content. So it also shows that even though this system got the most fertilizer applied, there's something in the soil that's being able to supply protein and nitrogen to the plant at a much higher level in the other systems. So there's more nitrogen actually built into the organic material. And this has an impact also on the economics of the system. So when we looked at between 2016 and 2021, 90% of all the wheat that was produced in the medic system and the cover crop system was bread grade wheat. But only 75% of the wheat from the cash crop only system was bread grade. So there's a significant difference in the amount of wheat that is good enough quality that you can sell it as bread grade wheat. Okay, now when we want to look at these systems overall, so they have a difference in performance, there's no difference in carbon sequestration ability, and there's no significant difference in nitrous oxide emissions. We did see a big difference in the spike. Okay, so we want to look at the global warming potential. So we took the results from the carbon and the soil emissions. Then we looked at all inputs, so fertilizer, pesticides, seeds, and fuel. Then we looked at direct emissions from livestock, and for this we used IPCC. Then we looked at indirect land use emissions as well as direct land use emissions, which is basically what is the impact of the carbon stored in lands. And then we wanted to compare different commodities. So for you to be able to compare one lamb with a certain amount of wheat, we used a grain equivalent. So this is a German metric, and this is basically we used a metric to be able to combine everything and almost change the currency of it all into grain equivalents. And then wool has no grain equivalent because it's not edible. So for this we used economic allocation, and this is just basically there's a certain amount of the emissions of livestock which we excluded because we allocated this towards the production of wool. Okay, so now looking at the results and the sources of emissions between the different systems. So the sources that differed the most were fertilizer, the amount of carbon sequestered, fuel usage, and nitrous oxide. So fertilizer is the biggest one. You can see that in the cash crop system, fertilizer is the hotspot of the system, which means that most of the footprint comes from the use of nitrogen fertilizer. And this is just because nitrogen fertilizer uses so much energy to be able to manufacture. It's very carbon intensive as an input. So there was a huge difference between the emissions that came from nitrogen fertilizer. Then the carbon sequestration, although this was not significantly different between systems, in all systems the amount of carbon that was being sequestered year on year was more than the amount of emissions emitted. So this just shows the importance of being able to build up the carbon in your soil. It really makes a difference in your overall footprint, and it's just an important thing to be able to manage. Then the other thing was fuel usage. There was a big difference in the fuel usage, and this is because when you have cover crops or meddocks and sheep, you aren't having to do as many tractor passes, and you aren't using as much diesel. So you're almost having what you call a dilution effect. So instead of using intensive tractor passes on all of your fields in all 4 years, you only have it maybe 3 years or 2 years. And then the last one was nitrous oxide. Now the difference from this is just because of that spike period, and although in this one there was more nitrous oxide emissions for the systems that had legumes and livestock in, the extra emissions that you save from not having to bring in nitrogen more than accounts for that. So by not using as much nitrogen fertilizer, you're saving 4 times the amount of the nitrous oxide increase. So it really is worth it to be able to fix your own nitrogen, even if it means you might have some spikes of nitrous oxide. And then another thing to note is the livestock emitted more greenhouse gases than any other inputs in the wheat medic system. So yes, livestock they do emit a lot of emissions, but it's still less than the amount that nitrogen would have emitted if you had to buy in the same amount of nitrogen that it's supplying to the system. Okay, and then when you look at the global warming potential of different commodities, which is basically for the different types of things you can produce for wheat, canola, and lamb, what is the carbon footprint per kilogram of that grain equivalent? So we had the highest global warming potential was for lamb. Because of the enteric fermentation, which happens in the stomach, so these emissions occur throughout the whole life cycle of the animal, the amount that a grain equivalent, it is very carbon intensive. And then the wheat and canola has a lower footprint, but there was a significant difference in the emissions of the same commodity when you produce it in different rotations. In other words, producing wheat in the first rotation system that only has cash crops versus producing it in the last rotation system meant that there was a significant difference in the carbon footprint of that product. Okay, and then another thing to note, although lamb has a much higher footprint than wheat, this is because you are comparing lamb to wheat. If we had to maybe compare different animal production systems, then that would be a better comparison. Okay, and now when we want to look at basically the results of this, we found that in all our different models, so we modeled for the different land use impacts. We also modeled for if you want to include the livestock emissions within your system, or if you consider it to be an animal production and should be separate. And we also did the carbon footprint for specific commodities. And basically we found, in summary, the system with the highest carbon footprint was the cash crop only system. And in comparison to this system, the system that had a cover crop, which is wheat, canola, wheat, and a cover crop mixture, there was a 35% reduction in emissions per product that you're producing. So for the amount that you're getting out of that system, you're having much less emissions. And a 50% reduction in emissions per hectare. So this is about the intensity. So it's giving a real mitigation of 15%, but it's also improving the product. Then with the MEDIC system, so wheat, MEDIC, canola, and MEDIC, there was an 11% reduction in emissions per product, which is the amount that you're outputting, and a 7% reduction in emissions per hectare, which is the area. But if you had to consider the pastures to be considered fodder production, so if you decided that you aren't producing livestock, but you're rather producing hay or fodder, then you wouldn't have to include the livestock emissions, and this almost halves your footprint, and it makes a huge difference. So basically, in conclusion, being able to incorporate a legume and that could fix nitrogen in your system and replace nitrogen that you would have to buy in, was a significant way to reduce your carbon footprint, and this worked in all the systems. If you had to add livestock, you're losing a bit of that savings just because of the livestock emissions, but infixation has a very high potential of improving the footprint and also reducing the cost. It also improved the protein content significantly, and also the yields. Then when you looked at the cover crops, even though you're sacrificing 1 year of the 4-year rotation, when you look at just the amount of wheat and canola you're producing in a 4-year cycle, even though it's on a quarter less of the land, it was still more just because of those ecosystem or rotation benefits to the system. So the cover crop system produced more wheat and canola in 4 years than a fully wheat and canola system, just because each year there was a significant increase in yield. Then soil carbon sequestration, this was very important in the systems and was able to reduce a lot of emissions. And then the last thing is just that increasing outputs and the efficiency is also important along with mitigation, because if you can produce more with less inputs, then you're decreasing your emissions per output. And then just the last note on livestock incorporation. Livestock are beneficial because they can convert forage and fodder that we can't eat into food products. And you can use this fact to be able to reduce the intensity of cropping systems by rotating a cash crop with a pasture phase. But most of the benefit wasn't directly from the livestock, that was indirect, but it was from nitrogen fixation. And then the last thing is, when you incorporate livestock, you have to do this carefully. If you incorporate too much livestock, then you're going to have overgrazing, and you could reduce your ability to fix in and also reduce the soil carbon sequestration. And then also just to take the context in mind, the swampland area is in the Renosterveld biome, which is a biodiversity hotspot, and being able to manage your grazing and not have that impact the Renosterveld is very important. And then the last thing is just that there's a massive carbon footprint saving if you can integrate livestock systems through existing producers. So in other words, if you can link with a neighboring farmer, if you produce different things, and instead of you having to incorporate different things into your rotation, if you can almost trade resources, or if livestock can come on your farm and do a bit of grazing, and you can get the benefits of the pasture and the ecosystem benefits without having to produce another commodity, then that has a massive saving just on your carbon footprint. Okay, so in conclusion, you don't want to view a crop rotation system as separate phases, but as one multi-year agro-ecosystem. So you want to look at ecosystem services as outputs that support the rotation. So yield isn't the only output, yield isn't the only thing you're producing on your farm. You're producing nitrogen for your other phases, you getting carbon into the soil, and you're improving the system. All those things benefit the rotation overall. And you want to be able to link different phases in the system together. So it's not just wheat and then canola and then medic and livestock. All these things are impacting each other. The nitrogen that you fix in the livestock year is feeding the wheat that you produce the next year. And in the same way, one rotation system is one big system that you're managing altogether. And that is basically what it comes to. How can you use linking different things to become more efficient and reuse resources? And this will improve both your productivity and can also improve your profitability in the long term. Okay, and then just a last word of thanks to all the project funders, and any questions can be directed to me via email. Thank you.